Welcome to our deep dive into some really mind-bending science today.
Absolutely.
We're looking at this incredible new research, basically letting scientists watch individual atoms, well, form bonds in real time.
Which sounds simple, but it's fundamentally difficult.
Right. So our mission today is to unpack how they did it, what they found, and, why it should matter to you.
And it really gets down to overcoming this huge problem.
Yeah.
How do you even see something so small happening so unbelievably fast?
Exactly.
This gives us this amazing window into energy transfer, charge transfer, right at the atomic level. Things we've only guessed at before.
Okay, so let's start there. The speed, normally atoms like magnesium, they just, snap together instantly?
Pretty much instantaneous, yeah.
Yeah.
It makes seeing the start of the process basically impossible under normal conditions.
So how did this team, it was led by Marcus Koch at TU Graz, right?
Yeah.
How did they get the atoms to just wait at the starting line?
Yeah, that's the million-dollar question, isn't it? How do you hit pause on something that happens in, like, a quadrillionth of a second? Their solution was, well, ingenious. They used superfluid helium droplets. Think of them as tiny, tiny nano-fridges.
Nano-fridges, okay.
Yeah, these things are unbelievably cold. We're talking just 0.4 Kelvin.
Wow, okay.
That's about minus 273 Celsius. Just a tiny fraction above absolute zero.
So practically frozen solid, but it's helium, so it's superfluid.
Exactly. It behaves like a liquid with zero friction, zero viscosity. And the crucial part is these droplets capture individual magnesium atoms. And they hold them apart, about a millionth of a millimeter apart, each atom isolated in its own supercooled little chamber.
So that gives them the stable starting point they needed, like lining runners up in their blocks.
Precisely. The perfect setup to initiate the reaction and watch it unfold.
Okay, that's amazing. So they've got the atoms chilled, isolated, poised, then they trigger it with a laser, right?
That's right. A laser pulse gets things started.
But then they sheet the observation part. How do you see something that fast? Even if they're starting from a standstill, the reaction itself is still incredibly quick.
Right. The bonding is still happening on the femtosecond timescale. That's a millionth of a billionth of a second.
Mind-boggling.
So they use something called femtosecond spectroscopy, combined with photoelectron and photoefficient analysis.
Okay, break that down a bit. Femtosecond spectroscopy.
Think of it like using an unimaginably fast strobe light. You hit the forming cluster with another laser pulse, incredibly short and precisely timed.
Freezing moments in time.
Sort of. This second pulse knocks out electrons and ions from the cluster as it's forming. And by analyzing those ejected particles, their energy, their direction, you can piece together what the cluster looked like at the exact moment the pulse hit it.
So you're not seeing the bond directly, but reading the evidence left behind by the laser pulse hitting it at different stages.
Exactly. It's like reconstructing a movie frame by frame, based on the snapshots provided by the ejected particles. Incredibly precise.
That is seriously clever. Okay, so using this technique, what was the big reveal? What did they see happening?
The really key discovery was this phenomenon they called energy pooling.
Energy pooling.
Yeah. So the first laser pulse gives some energy to several magnesium atoms in the forming cluster.
Okay.
But instead of each atom just holding on to its little bit of energy, they found that multiple atoms would effectively pool their energy together.
Pool it, like combine it.
Exactly. They transfer all that combined excitation energy onto one single atom within the cluster.
Whoa. So one atom gets a massive energy boost from its neighbors.
Precisely. It gets pushed into a much, much higher energy state than any single atom could reach on its own from the initial pulse.
Kind of like everyone chipping in to buy one big thing instead of lots of small ones.
That's a great analogy, yeah. And this is the first time this kind of collective energy transfer has actually been observed with time resolution. We could see it happening.
And that changes how we think about energy moving around at this tiny scale.
Fundamentally. It shows energy doesn't just dissipate randomly. It can be concentrated, funneled, very specifically.
Okay, wow, that's a big deal in fundamental chemistry. But let's bring it back to Earth a bit. This is amazing basic research, but are there, wider implications? Does this affect us?
Oh, absolutely. There's real potential here. First, the researchers hope this whole technique, using the helium droplets for isolation, could work for lots of different elements.
So it could become a standard tool for this kind of basic science.
That's the hope, a general method. But beyond that, this energy pooling discovery itself, well, understanding how to control energy transfer at the atomic level is huge.
How so?
Think about applications where directing energy is key. Photomedicine, for instance.
Okay.
Imagine designing light-activated drugs where you could pool the light energy precisely onto the active part of the molecule, making it way more efficient, maybe targeting specific cells better.
Right, more targeted therapy.
Or think about solar energy. What if you could funnel the captured light energy more directly to where it's converted to electricity instead of losing so much as heat?
Boosting efficiency. Potentially, quite a bit.
Potentially. It really highlights how digging into these super fundamental processes, things happening on scales we can barely imagine, can spark ideas for completely new technologies down the road.
So it's a reminder that even in something as basic as two atoms joining, there are these incredibly complex, elegant dances going on, these chilled atoms, waiting, then pooling energy in an instant.
Exactly. It's all happening constantly, all around us, just hidden from view until we develop tools precise enough to see it.
A fascinating peek behind the curtain.
It really underscores the power of precision, doesn't it? How looking at the smallest details can unlock really profound insights into energy, into chemistry, and, well, into its potential. Makes you wonder what else is waiting to be discovered at that level. What really jumps out at you from all this?